In the YouTube video titled Lecture 6, Data Encryption Standard, DES Key Schedule and Decryption by Christof Paar, Professor Paar begins by welcoming viewers to the 6th week of his Introduction to Cryptography course. He proceeds to provide a concise recap of the previous week's lecture, which delved into the fundamental principles of the Data Encryption Standard, DES, at a high level. This included outlining the process by which a 64-bit block is transformed into another 64-bit block through encryption. Professor Paar then transitions to the central theme of the lecture, the DES key schedule. He meticulously dissects the intricate process through which the initial 64-bit key is leveraged to generate a series of 16 subkeys, denoted as K1 to K16. He explains this process involves a sequence of operations, encompassing permutation choice, PC1, PC2, left shifts, and permutations. The lecture then transitions to the decryption process for DES. Professor Paar elaborates on how this process essentially mirrors the encryption process in reverse, with the subkeys being applied in the opposite order. He also emphasizes the near-identical nature of the rounds in DES, with only the input parameters undergoing variation. He then shifts the focus to a demonstration of how to reverse a single round of DES. This involves dissecting the round into its constituent components and illustrating how each can be reversed. Professor Paar acknowledges that this segment represents the most intellectually demanding portion of the lecture, but he underscores its critical role in fully comprehending the decryption process. The lecture continues by highlighting the inherent vulnerability of DES, which can be compromised within a matter of days through brute force techniques. Professor Paar stresses the importance of refraining from utilizing DES in contemporary applications. He proceeds to present a selection of alternative algorithms commonly employed in modern cryptography, including AES, Serpent, and RC6. Professor Paar concludes by expressing gratitude to viewers and underscoring that the subsequent week's lecture will center on AES, a more secure and widely adopted encryption algorithm. From 0 minutes to 5 minutes of the video, Professor Christof Paar introduces the 6th week of his Introduction to Cryptography series, dedicating this lecture to a detailed exploration of the Data Encryption Standard, DES, algorithm. Paar initiates the session by re-emphasizing the central role and versatility of DES, a 64-bit block cipher, which was discussed at length during the previous week. He underscores the critical importance of the key schedule in the algorithm, as it plays a pivotal role in generating a sequence of 16 unique subkeys, K1 through K16, from the original 64-bit key. He emphasizes that the security and efficacy of the encryption process hinge on the robustness of the key schedule. From 5 minutes to 10 minutes of the video, the speaker delves into the intricate details of the Data Encryption Standard, DES key schedule, focusing on the pivotal question of subkey derivation. He begins by outlining the procedure, commencing with the initial 64-bit key. This key is subjected to a permutation using PC1, a designated permutation table, resulting in a 56-bit key. The 8 discarded bits, known as parity bits, are intentionally omitted from the key schedule. This 56-bit key is then partitioned into 2 28-bit segments. Each of these segments undergoes a series of left circular shifts, a process referred to as rotations. These rotations are conducted in rounds, with the number of positions shifted varying between 1 and 2. Specifically, the 1st, 9th, and 16th rounds shift 1 position, whereas the remaining rounds shift 2 positions. The speaker emphasizes that the key schedule necessitates a total of 28-bit shifts, including 3 shifts of 1 position in the 1st, 9th, and 16th rounds, and 26 shifts of 2 positions in the remaining rounds. The next stage involves permuting these 28 bits using another permutation table, denoted as PC2. This permutation culminates in 48 bits, effectively reducing the key by an additional 8 bits. These 48 bits are of paramount importance, representing the final subkeys employed in each round of the DES algorithm. The speaker underscores that the subkey generation process, though complex, is deterministic. This deterministic nature means that a specific initial key will consistently yield the same set of subkeys. From 10 minutes to 15 minutes of the video, the speaker delves into the intricate process of the key schedule within the Data Encryption Standard DES algorithm. This pivotal step transforms a 64-bit key into 16 distinct subkeys, each playing a crucial role in the encryption rounds. The process commences with a permutation choice, PC1, meticulously selecting 56 bits from the original key, effectively discarding 8 parity bits. These 56 bits are then neatly partitioned into 2 halves, each comprising 28 bits. The speaker then elaborates on the left shift operation, a core aspect of the key schedule. This operation rotates these halves by 1 or 2 positions, the number of positions being determined by the round number. For instance, the 1st, 2nd, 9th, and 16th rounds shift by 1 position, while the remaining rounds shift by 2 positions. In total, the key schedule implements a left shift across 28 positions, 4 from the single-bit shifts and 24 from the 2-bit shifts. From 15 minutes to 20 minutes of the video, the speaker elaborates on the key schedule employed in the Data Encryption Standard, DES algorithm. He emphasizes that this intricate process takes a 64-bit key as input and, through a series of transformations, generates 16 distinct subkeys, each comprising 48 bits. The initial step involves permuting the key utilizing a predefined permutation table known as PC1, which results in a 56-bit key, effectively discarding 8 bits in the process. This is followed by segmenting the 56-bit key into 2 equal halves of 28 bits each, upon which a left circular shift operation is executed independently on each half. The speaker elucidates that the extent of these shifts, i.e., the number of bit positions shifted, is contingent upon the round number. Specifically, 1-bit position is shifted in rounds 1, 2, 9, and 16, while 2-bit positions are shifted in all remaining rounds. Finally, the 2 28-bit halves are concatenated and subjected to another permutation using a table designated as PC2, yielding a 48-bit subkey. This entire sequence of operations is replicated 16 times, resulting in the generation of all 16 subkeys. From 20 minutes to 25 minutes of the video, the speaker delves into the concept of decryption in the Data Encryption Standard, DES, emphasizing its role as the inverse of the encryption process. The speaker emphasizes that, while the majority of DES rounds operate with identical logic, the input parameters vary, making decryption the reverse operation. The crux of the challenge, the speaker asserts, lies in demonstrating how to reverse a single DES round. This understanding hinges on recognizing that the output produced by round 15 during encryption serves as the input for round 15 during decryption. The speaker then shifts focus to the overarching objective of proving the efficacy of the decryption procedure. This involves demonstrating the equivalence between the values of L1 and R1 and specific variables. The speaker underscores the importance of meticulous variable substitution and replacement in the process. Notably, the L15 value is shown to cancel out, leaving a simplified equation for R1, crucial to understanding the decryption process. The speaker concludes this section by summarizing the round-by-round reversal nature of decryption in relation to encryption. Specifically, they emphasize that round 16 in decryption serves as the inverse of round 1 in encryption. This section culminates with the speaker acknowledging the complexity inherent in comprehending the nuances of decryption and its inverse relationship with encryption. From 25 minutes to 30 minutes of the video, the speaker transitions to the second major topic of the lecture: decryption in the Data Encryption Standard, DES algorithm. He underscores the fundamental principle of decryption, emphasizing that it is the mirror image of encryption. Every round in decryption functions as the inverse of its corresponding round in encryption. To illustrate this concept, he focuses on the final round of encryption, round 16, detailing how to reverse its actions for decryption. This involves inverting the F function and exchanging the left and right halves of the block. The speaker then proceeds to explain that the decryption process is completed by applying the inverse of the initial permutation, IP1, to the final output of the decryption procedure. This results in the restoration of the original plaintext. He clarifies that, despite their seemingly identical nature, the F functions in encryption and decryption diverge in the sequence of operations they perform. He continues by demonstrating how to calculate the inverse of the F function, which entails utilizing the inverse of the S boxes and the inverse of the P box, effectively reversing the substitution and permutation operations executed during encryption. Furthermore, the speaker points out that decryption employs subkeys, which are the inverses of the subkeys utilized in encryption. He asserts that the key schedule in decryption mirrors the key schedule in encryption, the sole difference being the reversed order of the subkeys. This ensures that decryption effectively nullifies encryption, accurately restoring the original plaintext. From 30 minutes to 35 minutes of the video, Professor Paar delves into the critical concept of decryption, emphasizing the need to understand how the encryption process is reversed. He underscores the importance of comprehending round reversal, particularly focusing on how the reversal of round 1 enables the reversal of subsequent rounds. Through the use of visual aids, Professor Paar illustrates the key elements involved in round 1 reversal, guiding viewers through the process. He then proceeds to demonstrate the equivalence between L1, the left half of the 64-bit block following round 15, and R15, the right half of the 64-bit block after round 15. He further elaborates on the derivation of L1, showcasing its relationship to R0, the right half of the initial 64-bit block, and the output of the F function, denoted as F, K15, R0. Here, K15 represents the 48-bit subkey utilized in round 15. Professor Paar breaks down the equation to reveal that L1 is equivalent to the bitwise XOR operation of R0 and F, K15, R0. He stresses that grasping this intricate connection between L1, R0, and F, K15, R0 is essential for comprehending the mechanics of DES decryption. From 35 minutes to 40 minutes of the video, Professor Paar delves into the intricate process of decryption within the Data Encryption Standard, DES, specifically focusing on the reversal of the initial round. He posits that decryption effectively mirrors the encryption process, but employs a fundamentally identical logic and set of operations. To elucidate this, Professor Paar meticulously dissects the steps involved in reversing the initial round through a visual representation, highlighting the crucial variables that govern the process. He utilizes a color-coded notation system to delineate the left, L, and right, R, halves of the data block during the decryption operation, enhancing clarity and visual understanding. Professor Paar formally articulates the overarching objective as demonstrating the equivalence of L1 and R1, the outputs of the first round of decryption, to specific variables. This objective serves as a foundational proof of the decryption process's ability to successfully reverse the initial round of encryption. Professor Paar then introduces L15 and R15, representing the inputs of the final round, and L1 and R1, representing the outputs of the initial round of decryption. Continuing his in-depth analysis, Professor Paar underscores the equivalence of L15 to R15, implying that the left and right halves of the data block are congruent prior to the execution of the final round. He subsequently introduces a variable aptly named Ki, which represents the input to the F function during the final round. The speaker methodically demonstrates that L1, the output of the first round of decryption, can be expressed as the sum of L15, the F function of Ki, and R0. Analogously, he illustrates that R1 can be expressed simply as L15. This detailed derivation provides a compelling demonstration of the successful reversal of the first round of encryption by the first round of decryption, effectively validating the functionality of the decryption process as a whole. From 40 minutes to 45 minutes of the video, Professor Paar elucidates the crucial concept of decryption within the DES algorithm, emphasizing the need to demonstrate its reversibility with respect to the encryption process. This entails proving that decryption effectively inverts the encryption steps. To illustrate this, he focuses on the final round of encryption, denoted as R15, and its corresponding decryption counterpart, labeled as R1D. The professor then introduces relevant variables for a clear understanding of the process. He identifies R15 as the output of the F function, which also serves as the input for the initial permutation IP in the preceding round. This crucial linkage implies that L15, representing the left half of the data block, is equivalent to R1. Further enriching the analysis, he introduces the variables Ki, the key utilized in the F function, and R0, the right half of the data block prior to the F function. He emphasizes that L0, the left half of the data block in the round preceding the F function, is equal to R0. Professor Paar proceeds to demonstrate how L1 can be expressed in terms of these variables, tracing its origins back to L0. Specifically, he states that L1 is equivalent to L0 augmented by the output of the F function. This relationship is succinctly represented by the expression L0 plus F, Ki, R0. He further elaborates that R1 is equivalent to L0, which simplifies to the equation R1 equals R0 plus F, Ki, R0. This insightful observation underscores the reversibility inherent in the decryption process as it mirrors the encryption process by inverting the F function and the permutation steps. Finally, he clarifies that by substituting R0 for R1 in the formula for L1, the equation becomes L1 equals R1 plus F, Ki, R0, thus conclusively demonstrating the reversible nature of decryption and encryption in the DES algorithm. From 45 minutes to 50 minutes of the video, Professor Paar delves into the intricacies of DES decryption, meticulously demonstrating the reversibility of each round. He commences by establishing the equivalence of L1 and R15, a crucial step in unraveling the encryption process. Subsequently, he derives the expression for R1, emphasizing its dependence on L15 and the output of the F function with inputs Ki and R0. Professor Paar, cognizant of the potential for confusion, meticulously clarifies the index notations, emphasizing their role as mere substitutions rather than complex operations. Moving forward, he addresses R0, equating it to R15 and highlighting the substitutive nature of the F function application in the preceding step. To illuminate this substitution, he presents the equation and cancels L15 from both sides, resulting in a streamlined expression for R1. The final segment of this interval focuses on the decryption of round 15, emphasizing its inverse relationship with the encryption of the same round. The discussion culminates in the assertion that round 16 of decryption effectively reverses round 1 of encryption, solidifying the cyclic nature of the DES algorithm. From 50 minutes to 55 minutes of the video, the speaker delves into the intricacies of DES decryption, focusing on the crucial step of reversing round 15 of encryption. He emphasizes the fundamental principle that decryption entails a systematic reversal of the encryption rounds. To illustrate this concept, he uses the specific example of round 15, demonstrating how the output, L15 and R15, can be expressed in terms of the input, L14 and R14. Utilizing a pedagogical approach, the speaker employs color coding to provide a visual representation of the decryption process. The output of the F function, which takes as input the subkey K15 and R14, is added to L14 to produce L15. Simultaneously, R14 is directly transferred to R15, effectively establishing the input for the subsequent round of decryption. He underscores the crucial property of the F function as a deterministic function. This means that given identical inputs, K15 and R14, the output will consistently remain the same. This deterministic nature of the F function is central to the understanding of how decryption systematically reverses the encryption process. Concluding this segment, the speaker reinforces that the decryption process for the remaining rounds, 14-1, adheres to the same logical framework, effectively reversing the encryption process until the original plaintext is retrieved. From 55 minutes to 60 minutes of the video, Professor Paar delves into the concept of a brute force attack, wherein an attacker systematically attempts to decipher ciphertext by iterating through every possible key. He underscores the magnitude of the key space in DES, encompassing 2 to the power of 56 potential keys, making a brute force approach computationally infeasible within a practical time frame. He highlights the Electronic Frontier Foundation's landmark achievement in 1998, where they successfully cracked DES through a brute force attack, albeit with the aid of a custom-built machine and a time investment of approximately 90 minutes. This event marked the formal obsolescence of DES as a viable cryptographic standard, signifying its vulnerability to advanced computational resources. Professor Paar briefly transitions to the Advanced Encryption Standard, AES, a contemporary block cipher widely recognized for its enhanced security. He emphasizes AES's resilience against even formidable attackers, attributing this strength to its considerably larger key space, which further complicates the feasibility of brute force attempts. However, Professor Paar cautions that even AES is not completely impervious to attacks. He explains that incorporating multiple rounds of encryption with distinct keys introduces substantial complexity, significantly bolstering security and mitigating potential vulnerabilities. He concludes the segment by asserting that DES, despite its current obsolescence, played a pivotal role in shaping the evolution of modern cryptography. Its shortcomings ultimately spurred the development of more robust algorithms like AES, ensuring the ongoing advancement of secure communication technologies. From 60 minutes to 65 minutes of the video, Christof Paar delves into the decryption process of DES, Data Encryption Standard, elucidating that it fundamentally mirrors the inverse of encryption. He emphasizes the principle of round inversion, where each round of decryption functions as the inverse of its corresponding encryption round. Paar meticulously illustrates this concept by dissecting the decryption process stage by stage, highlighting the crucial role of round inversion in ensuring the reversibility of the algorithm. He underscores the objective of demonstrating the efficacy of decryption by establishing congruence between the decryption output and the encryption input. Specifically, he concentrates on substantiating the equivalence of L1 and R1, variables representing the left and right halves of the data block following a single round of decryption. Paar employs visual aids to elucidate the pivotal operations involved, including the inverse F function, which processes the right half of the data block, R1, in conjunction with the subkey, K1, generated by the key schedule. Paar then proceeds to combine the outputs of the inverse F function and the left half of the data block, L15, to derive the left half of the data block in the preceding round, L1. This step concludes with the exchange of the left and right halves of the data block, culminating in the original state of the decryption process. This sequence effectively demonstrates the capability of decryption to reverse the encryption process. From 65 minutes to 67 minutes of the video, Professor Paar transitions from explicating the intricacies of the DES key schedule and decryption to a discourse on the practical implications of cryptographic security. He introduces the concept of a brute force attack, an exhaustive method of decryption that involves systematically testing every potential key until the correct one is identified. This technique, while theoretically viable, is computationally demanding and becomes infeasible as the complexity of the key space escalates. Professor Paar emphasizes the historical significance of the brute force attack on DES, highlighting that this event signified a watershed moment in the field of cryptography. It underscored that even a seemingly robust cipher like DES could be susceptible to cryptanalytic efforts, particularly when aided by specialized hardware designed for this purpose. This development served as a stark reminder of the ongoing arms race between cryptographers and attackers and the need for continuous innovation in cryptographic design. Professor Par's discussion then pivots towards the ramifications of this attack on the security of DES and other ciphers. He underscores that the brute force attack on DES exposed its vulnerabilities and spurred the development of more robust encryption standards. He cites the Advanced Encryption Standard, AES, a block cipher widely considered secure and efficient, as a prime example of this evolutionary response to the limitations of DES. In concluding this segment, Professor Paar emphasizes the dynamic nature of cryptography, characterized by a perpetual interplay between the development of novel cryptanalytic techniques and the creation of more robust cryptographic solutions. He highlights the crucial role of this ongoing competition in safeguarding secure communication and protecting sensitive data in our digitally reliant world. He underscores the imperative of transitioning away from vulnerable algorithms like DES and adopting more resilient encryption standards to safeguard vital information in today's digitally pervasive environment.